In this section of chapter 6, I would like to go over particle nature of radiation or energy and photoelectric effect. Planck's theory tells us that energy is emitted or absorbed in whole number multiples of h nu. So in other words, substances absorb or give off radiation in a quantized or discrete manner, like 1 times h nu, 2 times h nu, or 3 times h nu. H has a fixed number, 6.63 times 10 to the negative 34 joules second. Let me explain that to you. If, say for example, I have a sample here that absorbs radiation, and the particular radiation that's falling on that object is shown. From this radiation is going to absorb, the substance absorbs at least 1 times h nu, which is 6.63 times 10 to the negative 34 times the frequency of the radiation falling on that object, or 2 times that value or 3 times that value, but never a fraction of that value. And that's called quantized energy. So absorption or emission of radiation happens in a quantized manner rather than a continuous manner. Now here we are showing you the analogy between walking up steps and walking continuously up. So quantum is pretty much like what you see on the left hand side, as if it's like steps or some packets or discrete amount of energy. Now, what is photoelectric effect? When radiation or light shines on a metal that you see on the top, then you know that metal is made up of all these electrons, and those are loose electrons. They have also protons. When radiation strikes metal, electrons are knocked off, and that's what you're seeing here, and that's called photoelectric effect. And we're going to show you more specifically the observations made in these experiments, and Einstein explained photoelectric effect by assuming that radiation is made up of particles, which is called photons, and photon energy is given by h times frequency, where h is 6.63 times 10 to the negative 34 joule times second. Here are the observations, experimental observations of photoelectric effect. Energy of ejected electrons depends upon frequency of radiation. Remember, I mentioned that frequency is related to energy. So having larger frequency means the radiation has more energy to begin with. So ejected electrons depends upon the energy carried out by ejected electrons depends upon the frequency of radiation. So larger frequency of radiation means larger amount of energy will be taken up by ejected electrons. In order to explain this, Einstein assumed radiation to be made up of photons, or tiny radiation particles. Each photon has the energy of h times frequency. Again, h is a fixed number, so depending upon what radiation or wave is, or radiation, or what kind of radiation is striking on the metal plate, the photon energy is going to be different. Like X-ray, photon energy would be much greater than blue light photon energy, because X has much larger frequency. So as you can see from this expression, the larger frequency gives a larger photon energy, as h is a constant. Now here we are explaining the outcome when radiation strikes a metal, that has all these electrons bonded. Now in this simple analogy, let's assume that object A is glued onto a surface of a metal, and the binding energy is 8 joule. That means it is bonded to the surface with 8 joule of energy, and to remove it you need to apply at least 8 joule. On the left hand side, you are striking this object A with an object B with 5 joule of energy. When 5 joule of energy, the ball B strikes A with 5 joule of energy, is it going to eject A? Answer is no, because 5 joule doesn't provide sufficient energy. On the other hand, in second case, you're throwing a ball with 10 joule of energy, and as soon as it strikes A and transfers its 10 joule of energy to A, this particle is going to move away because it needs 8 joule of energy to break the bond. So how much would be kinetic energy? How much energy it would be taken up as kinetic energy? It would be 10 minus 8, because 8 would be used up in breaking it loose, and then the rest of the energy would go and move the particle, so it would provide the kinetic energy. So 10 minus 8, 2 would be the amount of energy taken up by A and would move away from the surface. Now we can now replace these with mathematical expressions that I'm going to show you in next slide, which is very important to understand that 2 joule represents kinetic energy of ejected electron, in our case when electron will be ejected. 10 joule represents the energy of a striking particle, which could be a striking photon, and 8 joule represents binding energy. So keep that in mind. E kinetic, so I can write down kinetic energy will be given by incoming particle energy, and in our case it's going to be photon energy, minus binding energy. Let's use B for binding energy. Okay, the same thing we're showing you here again. Kinetic energy would be given by photon energy minus binding energy, and photon energy is given by h times frequency. And we're going to do a problem that would apply this expression. Let's begin with problem number 31, page 242. In problem number 31, they're talking about a metal, and they're saying that that metal, so let's draw a metal surface, and keep in mind this has electrons bonded to the metal, so I'm just showing you one of them. The molybdenum metal must absorb radiation with a minimum frequency of 1.09 10 to the power 15 per second. So minimum frequency, remember, frequency is related to the energy of radiation. So minimum frequency means minimum energy. You just need to multiply by h to get the energy value from frequency. So let's write down these values. 1.09 times 10 to the power 15. 10 to the power 15 per second. So 1.09 times to the power 15 per second. Then let me rewrite this thing, doesn't look good. 1.09 times 10 to the power 15 per second. So that's the minimum frequency needed. From here we can get the minimum energy, and that would be the binding energy. So this radiation that is falling on it must have that kind of energy to eject this electron. So binding energy, this is part A. Binding energy would be given by h times minimum frequency that they have given you. And h has a fixed number, which is 6.63 times 10 to the power minus 34 joule times second, but the h value, which is a constant, times the frequency, which is 1.09 times 10 to the power 15 per second. And this would give you 7.23 times 10 to the negative 19 joule. Because second per second would cancel out, that would give you 7.23 times 10 to the negative 19. So from the information given, we calculated the minimum energy needed to eject that electron, and that minimum energy is 7.23 times 10 to the negative 19 joule. Now we're going to do number 31b. So 6.31b. The question is, what wavelength of radiation will provide a photon of this energy? We're talking about the minimum energy. Let's copy that number from the last slide. So the binding energy that we got, let's write down binding energy from part A equals to 7.23 times 10 to the negative 19 joule. So that's the binding energy. Now, in this case, we need to get the wavelength. So first write down energy equals to h nu, which is hc over lambda. So that's the energy expression. Now this is the binding energy, obviously. And then I can write down from here by simple algebra, lambda equals to hc over E, where E is the binding energy. So I'm going to replace that by BE, or binding energy. Now this expression is true for any energy. So let me now plug in those numbers. Lambda equals to, H is 6.63 times 10 to the negative 34 joule times second, and C is 3.00 times 10 to the power 8 meter per second, and at the bottom you need binding energy. So binding energy would be given by 7.23 times 10 to the negative 19, because this is the energy for which you're calculating the wavelength. That means that wavelength has to provide this much energy. Keep in mind, wavelength means it comes with a frequency, and a frequency means that comes with the energy. H times frequency is the energy. So this is, let me write down at the bottom, binding energy. And make sure you calculate your final answer here, and let me show you after cancellation what is left. Joule would cancel out, second per second would cancel out, and we get the right unit, which is meter. And make sure, try this. And I got 2.75 times 10 to the negative 7. Make sure you double check this. Now we're going to do number 31C. So this is going to be C. The question is, if molybdenum, so this is molybdenum surface, if molybdenum is irradiated with a light of wavelength of 120 nanometer. So 120 nanometer is striking the metal, and the question is, what is the maximum possible kinetic energy of the emitted electron? So find out what is the kinetic energy. We just discussed that, I think 2 or 3 slides back, that how we relate kinetic energy with incoming photon energy and binding energy. So let me write down that expression first. Kinetic energy of electron, E kinetic, is be given by incoming photon energy, or light that is shining on. So let's write down E photon energy minus the binding energy. Again, I need to get the value of binding energy from the last problem. So let me write down binding energy equals to 7.23 times 10 to the negative 19 joule. So let's have a line here. Okay, now they're giving 120 nanometer, so from that nanometer I can calculate the energy. So let's convert 120 nanometer to energy, which will be given by energy of incoming photon. So this is incoming photon, and we can write down that as hc over lambda, and minus the binding energy, which we already know. Now let's see what you get for energy of the photon. 6.63 times 10 to the negative 34 joule times second times C, which is 3.00 times 10 to the power 8 meter per second. And the lambda is 120 nanometer. 120 nanometer. See, nanometer doesn't match with meter, so we'll have to change it to meter. So let me show you the conversion at the bottom. So nanometer at the bottom and meter on the top. 1 nanometer, nano means 10 to the negative 9, so you should read like this on the top. Nanometer, 10 to the negative 9 meter. So now you can see what gets cancelled out and what doesn't. So nanometer cancel out. Meter on the top, meter on the bottom would cancel out. And you can see here per second cancels out to seconds, so it gets joule, and that's the right unit. And make sure you do the math and find out the kinetic energy of ejected electron.